This is my Precalculus course. Today we're going to learn some applications. If you haven't done the homework completely incorrectly from the last class, do that homework before watching this video. So we have some special bases here. In the problems that we did previously where we had logarithms, we didn't use these special bases because I didn't want to complicate things, but now we're going to use logarithms with base 10 and base e values. And the reason that base 10 is a special base is because it's very easy to work with because our number system is based on 10. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 symbols before those symbols repeat. So it's easy to work with base 10 exponential expressions and logarithms, so that's a very important base. We also have base e. Now e is just a constant. It's a non-repeating, non-terminating decimal, which simply means it's an irrational number. And this number is used as a base because in nature and in all kinds of applications we find that this number pops up, even in things like finance. Now, remember, log base 10 of x is abbreviated as log x. And log base e of x is abbreviated as ln x, and we call it natural log x. We learned this in my intermediate algebra course. If you forgot, that's okay. We're just doing some review here. And you may need the exponent rules, so I want you to take a picture of both these pages and have them right in front of you during the class today. We learned all this information in my intermediate algebra course. So now we're going to do some review. We're now going to solve exponential equations with special bases. Again, we did this in my intermediate algebra course. And I want you to write the Roman numeral of the exponent rule that you use in the margin. That'll help you remember the rules. So we have an exponential equation, but notice we have a special base. This e here is not a variable, it's a constant. It's Euler's number. And so we're going to solve this exponential equation, and we're going to use exponent rule number 1. When you multiply powers, we're multiplying, right? You add the exponents. So we get e to the 4x. Okay, and at this point we're stuck. There's nothing we can do unless we know how to translate from an exponential equation to a logarithmic equation. We can't solve this without a calculator because it requires advanced mathematics. But we have to know what to tell the calculator. Well, we have special notation. If we want to figure out what the exponent is, we tell the calculator log base e of 7. That's the notation we enter into the calculator. But remember, when you have log base e, we have special notation. We call that ln 7, natural log 7. Because again, e is used in a lot of applications that apply to nature. So now we're going to divide both sides by 4, and we get x is equal to natural log 7 over 4. And now all we have to do is go to the calculator, and I want you to push the ln button on your TI-84 Plus. If you're using a different calculator, then you may have to enter 7 first and then push the natural log button. But if you're using a TI-84 Plus, and by the way, let's press the green alpha button at the upper left, and then at the far upper left, y equals button, the stat plot F1 y equals button, and then press enter, and now we've got a fraction template. So that's very, very useful in the math curriculum to know how to create a fraction template like this. And now I want you to press the ln button at the bottom left or middle left, then 7, then right parenthesis, then down arrow key, then 4, and then enter. And you should get 0.486. Because it says up here, round to the nearest thousandth if necessary. So if you had trouble with that, that's okay. Just go online to try to figure out how to do this with your calculator. Remember, in this class we use a TI-84 Plus, not because it's the best calculator necessarily, but it's just the most common one that students use, so that's the one I'm showing students how to use. There are so many different types that we can't stop and explain every single type of calculator, so you'll have to figure that out on your own. So now we're going to use Roman numeral 2, exponent rule number 2, because we're dividing the powers. And if we divide powers, we subtract the exponents. So we have 10 to the 2x is equal to 8. So at this point, we're stuck. There's nothing that we can do unless we know how to translate from an exponential equation to a logarithmic equation. That's the most important thing when it comes to logarithms, is to translate back and forth between the exponential form and the logarithmic form. If you can't do that, then you have no chance of ever really being able to do problems with exponential expressions or logarithms. So we can't do this with the calculator, and that's why we need this notation. The exponent is equal to log base 10 of 8. So that's just what we tell the calculator to help us find this. Don't overthink this. Don't overthink this notation. It's just an expression that we that tells our calculator what to do. That's all. So now we well, before we do anything, let's change to log 8. Why did I change from log base 10 to log 8? Well, because remember, when you write a base 10 logarithm, you don't write the 10. It's just left off there. Because base 10 logarithms are so common that mathematicians just choose not to write the base, and it's just assumed to be 10. It makes things easier. Oh, whoops. Sorry about that. That should be a 2. Okay, so now let's get our calculators out, and I want you to understand very clearly that you can do this without using your green alpha button to get a fraction template in your calculator. If you're not using a graphing calculator, then it's going to be a lot more difficult for you to do this type of stuff, because you'll have to use parentheses. Now, if you're using a TI-84 Plus or any kind of graphing calculator, you can do this without a fraction template. And when I say fraction template, I mean this here. You can do it, but you have to use parentheses, and it's much more dangerous because there's a very good chance that you won't enter it in properly. So it's best to use the green alpha button at the upper left, then the y equals button at the far upper left, then press enter. And then we can enter in, press the LOG button at the middle left, and then 8, and then right parenthesis, and then down arrow key, and then 2. Make sure you stop and you can do that. Play around with your calculator, have fun with your calculator until you figure out how to do this, because you're going to need to be able to do this at some point. You're going to need to be comfortable with your calculator. If you're not comfortable with your calculator, then it's pretty much useless. So stop the video if you need to, and make sure that you can do that with your calculator. If you're having trouble with your calculator, that's okay. That's normal. Every student has trouble with their calculators. It takes a while to get used to it. So now I want you to try number 3, and when you come back, we'll do it together. Okay, we're back. So if you got that right, excellent. Go ahead and try number 4, and when you come back, we'll do it together. Alright, we're back. 0.418. So if you got that right, excellent. Okay, so now we're going to go on to a different type of exponential equation. It's still an exponential equation because we have a variable in the exponent, but these are just slightly different. All we have to do here really is just isolate e to the x, which is the same thing we did in the previous problems, but it didn't really require the typical algebra that we do. So we're going to subtract 1 from both sides of the equation. And this is a step that tends to confuse students, so I'm going to show this step. I didn't show dividing, or I didn't show subtracting 1, but I am going to show the division here because students tend to get confused by this. So we have 9/2 is equal to e to the x. And this is the crucial step where we need to understand that all we're doing is just telling our calculators what to do. We need to tell our calculator log base e of 9/2. But remember, log base e is abbreviated as ln, natural log. So all we have to do now is go to our calculator and press the ln button, then the green alpha button. Actually, we don't need the green alpha button, I guess. Clear out, press ln, then 9 divided by 2, then right parenthesis. That should be good enough. So you want to use the green alpha button to lead you to your fraction template when there's the potential for confusion. So again, we're rounding to the nearest thousandth place. Okay, so that was a base E problem. Now we're going to do a base 10 problem. And notice we had to use our special notation down here. So let's go to a base 10 problem. Now we're going to subtract 4 from both sides. And then we're going to divide both sides by 6, and I'm going to show the division because, again, this seems to confuse students a lot. So, dividing both sides by 6, and we have 10 to the x is equal to 2. And this is the crucial step where a lot of students get stuck. We just need to know what to tell the calculator. We're going to tell the calculator log base 10 of 2. But remember, if we have a base 10 logarithm, we don't write the 10, we just write log 2. So again, you can skip this step. I just wrote that so you know what log 2 means. So now we go to our calculators, and we press the LOG button in the middle left of your TI-84 Plus, then enter 2. And press enter. The calculator allows you to come up with a value without writing the second parenthesis, even though technically you should because it's not proper notation to write only a left parenthesis. Okay, so I want you to try number 7. When you come back, we'll do it together. Okay, we're back. Again, we're rounding to the nearest thousandth place, so if you got that right, excellent. Try number 8. When you come back, we'll do it together. Okay, we're back. There you go. So if you got that right, excellent. Okay, so now we're going to go in the opposite direction. We had to use logarithms to help us solve equations. Well, now we're starting with logarithms, and we're going to have to use exponential equations to help us solve the problem. So we're kind of going backwards here. Instead of an exponential expression, we have a logarithmic expression here. And let's solve this. So the way we do this is similar to the way we solve a lot of algebraic problems. We just solve for this logarithm. Isolate the logarithm. So add 5 to both sides. And actually, before we do that, these logarithms have special bases. So before we do anything, I'm going to write it as log base 10 of x. You don't have to do that, but it helps us see what the base is. Because there's no base here, it has to be base 10. Remember, base 10 is written without the 10. Base 10 logarithms. So now we're going to add 5 to both sides. And then we're going to divide both sides of the equation by 2. And then we get log base 10 of x is equal to 5. And now this is the point where we get stuck. There's nothing really that we can do unless we know how to translate from a logarithmic equation to an exponential equation. Remember, translating between those two forms is the most important thing when it comes to logarithms and exponential equations. So this little number here is always the base. Whatever the logarithm is equal to is always the exponent, because that's what a logarithm is. It's an exponent. And whatever's inside the log function goes on the other side of the equation. This is just definition. It's by definition. Don't waste your time trying to understand this. It's just notation that we use for the exponent in an exponential equation. It's just notation that we use to tell our calculators what to do. But mathematicians like to, well, they get excited about the notation, and so they give you problems where you have to translate back and forth. And so, again, don't overthink this. It's not something that's intuitive. It's just a notation that's been defined by mathematicians. So now we have 10 to the 5th power, and that's going to be 100,000. So there you go. So we had a special base in that logarithm as base 10, but the number didn't appear, because when you have a base 10 logarithm, the 10 doesn't appear. Well, now we have ln x. What does that mean? Well, that means log base e of x. So it's very important that you're able to translate so that we can understand what that ln means. That's the most important thing. So now we're going to isolate this logarithm. That's how we solve these equations. We're going to subtract 15 from both sides. And then we're going to multiply both sides of the equation by -3. And I'm going to show that. You don't have to show it, but I'm going to show that. And when I multiply, I have to use parentheses around the -2, right? Or else that's going to be false. So now we have 6 is equal to log base e of x. And this is the point where we get stuck. We don't know what to do unless we can translate to an exponential equation. So the base is e. It's always that little number there. The exponent is always what the logarithm is equal to, because that's what a logarithm is. It's an exponent. And whatever's in the log function goes on the other side. So now we could leave the answer like this. It's probably best to leave it like that. But we're told to, actually we're not told to round off, so I guess we can leave it like that. But I want you to understand that this is, E is not a variable, it's a constant. So let's go ahead and calculate this. So I want you to press the blue second button in your TI-84 plus, and then the divided by button. Actually, let's not do that. Let's push the clear out and push the blue second button, and then push the ln button at the middle left. And do you see that? It has a fraction, or it has a template like this. And then you can enter 6, and then press enter, and then we get our answer. So if you're using a different calculator, then well, there's all kinds of different ways that you have to do it. Sometimes you have to enter 6 first, then press the e to the x button, so it just depends. That's all things that you need to figure out. So we have 4, 2, 9. And I'm going to clarify. I want you to round off to the nearest hundredth. So I rounded to the nearest thousandth. So that should be 40, 43. Okay, so again, we're just going in the opposite direction here. This is all review. We've done this before, but if you're rusty, again, that's okay. So I want you to try number 11. And what you're going to do is you're going to isolate, and if I were you, I would change ln x to log base e of x immediately, just so you know what that means. And you want to isolate the natural log, or the log base e of x. Try number 11. When you come back, we'll do it together. Alright, we're back. So we give it a special letter. If you got that right, excellent. If you forgot to write the Roman numeral of the exponent rule, that's okay. But just be aware that we may be using some exponent rules with these problems. So try number 12. First thing you want to do is change log x to log base 10 of x, right? And then isolate log base 10 of x. Try number 12. When you come back, we'll do it together. Okay, we're back. Okay, so if you got that right, excellent. So we did some review with base e and base 10 expressions. Now we're going to do some applications, because base 10 and base e logarithms and exponential expressions, they have quite a few applications. So we talked about the magnitude of an earthquake in my my intermediate algebra course, and I think we talked about pH. pH and the magnitude of an earthquake, they both use base 10 logarithms. And we talked about base e applications also, but we're going to get to those. So now we're going to use base 10 expressions to measure the loudness of things, the sound perceived by the human ear. That's called loudness. So the loudness of sound is defined to be 10 times log of 10 to the 12th times x. I know that that's kind of a confusing equation there, but that's the loudness. And x is called the intensity of the sound, and it's measured in watts per square meter. So watts are a measure of power. A watt is the amount of power. Power is how much work you can do in a given amount of time. And you're going to learn all this when you take a college level physics course. So the intensity of the sound is measured in the power that the sound exerts per square meter, which is not something that's easy really to study, but physicists have figured out ways to measure the intensity of the sound, and we then use this equation to come up with a number that represents the actual loudness to our ear. So I know that this is kind of strange, but let's do some practice problems. Given the following intensities of sound, find the loudness perceived by the human ear. So this number here is x, and we're going to find L of x. So L of x is L of 10 to the negative 8. And by the way, this is function notation. And we don't see a base on that logarithm, right? There's no base. So what is the base if there's no base? It's 10. So that's why I wrote 10 there. So, oh, I forgot to enter in the x value. That's 10 to the negative 8. Okay, so I plugged in my x value there. I just copied this there. And that base wasn't there, but I wrote it. And so do you see how we're using this formula here? And the intensity of the sound is conveniently written as a base 10, which makes it to where we can do this pretty easily using the exponent rules. So these numbers are so small that you have to write them as base 10 because it would be really difficult to write them otherwise. So now let's use exponent rule number 1. And I'm going to write the exponent rule there so we know. We're going to combine these because they're both base 10, right? So we can just combine those. And we get 10 to the 4th power. That's exponent rule number 1. We're just multiplying the powers and we're adding the exponents. So now we need a, well, we could use a calculator, but we actually don't need to use a calculator. And let me show you why. Remember logarithm property 2? If these numbers are the same, if you have an exponential expression inside a log function, and the base of that exponential expression is the same base that you see in the logarithm, then the logarithm is just equal to whatever the exponent is. And I know what you're thinking. You're thinking, well, why is that? Well, it's pretty easy to prove. All we have to do is use the notation that we're familiar with for converting between exponential form and logarithmic form. So I'm going to set this equal to y, because we don't know what it's equal to. We're trying to prove that y is equal to x, right? But we haven't proven that yet. So let's translate this to an exponential equation, and then we'll have proven the property. It's really simple. Again, it's just based on the notation. So let's translate this to an exponential equation. What is the base? Well, remember, the base is always that little number there. The exponent is always what the logarithm is equal to, which is y. And whatever is in the log function goes on the other side. So what does this prove? These expressions are equal, right? These green expressions are equal. So if they're equal, what does that mean? Well, if the bases are the same, obviously y would have to be equal to x. But if y is equal to x, we can just change that y to x. So we proved it. We proved the property. Now, I know that's very strange. That's very, very, very strange. It's hard to get your head around that. But again, the reason it's hard to wrap your head around that is because all it is just notation we use to tell the calculator what to do. So we're just exploring the notation. We're not really exploring the concept. We're just simply exploring the notation. So don't waste a lot of time trying to understand the concept. You're just using particular notation. So what this means is because these two bases are the same, and you can get a picture of this if you want to. Because these two bases are the same, this entire logarithm becomes 4. I know that's hard to believe, but this entire yellow logarithm just became 4. And the green 10 is still out there like that. And then we have 40. Now, loudness is measured in, well, we name the units decibels. I'm sure you probably heard that word before. And decimals are abbreviated with lowercase d and then an uppercase b. So what is the loudness? It's 40 decibels. Okay, so let's try another one of those. The intensity of the sound is 10 to the negative 10 watts per square meter. And again, notice we're using function notation. You see this? This means that we're plugging in an input into the function, and the output is going to be L of x. The input is x, and the output is L of x. I know that's very confusing. So we're going to use our formula, and remember there's no base in the logarithm, so that means it's base 10. So we have 10 to the 12th times 10 to the negative 10. And remember, we have to simplify the inner part. So we're going to use exponent rule number 1 to combine these purple expressions. When we're multiplying powers, we just add the exponents and we get 10 to the second power. But remember, because these two red bases are the same number, this entire logarithm just ends up equaling 2. So this entire blue logarithm just became 2. And the 10 is still multiplied by the 2. So we have 20. And I'm going to need to find some more room here because we have to write our units, 20 decibels. So as you can see, this is pretty easy. This is just how we measure the loudness of sound. Again, in my intermediate algebra course, we studied how to measure earthquakes and how to measure the pH of water. But now we're measuring the loudness of sound. So let's do one more of these problems real quick before you try one on your own. So we're plugging in 10 to the negative 14th to our function. And our function is a log base 10 function. We always have 10 to the 12th multiplied by whatever the intensity of the sound is. We're going to use Roman numeral number 1 or exponent rule number 1 because we're multiplying the powers. So 10 to the 12th times 10 to the negative 14th is 10 to the negative 2 power. We just add the exponents. So now notice that these two, let's see, let me get a different color here. Notice that these two bases are the same, so the entire logarithm just becomes negative 2. So I know it's hard to believe, but that entire logarithm just became negative 2. And the 10 just kind of hangs out in front, so we have negative 20. So in this case, we actually had negative decibels. But how can we have negative decibels? Well, you know what that means? It means that we can't hear it. There's no sound there. That's all that means. If you have negative decimals, that means we can't. It's not loud. It's not even a peep. We can't even hear it. Okay, so I want you to try number 16, and when you come back, we'll do it together. Okay, we're back. So L of 10 to the negative 12 is equal to 10 times log base 10 of 10 to the 12th times 10 to the negative 12. And so now we're going to use exponent rule number 1. Add the exponents and we get 10 to the 0 power. And so now we have to use exponent rule number 7, which tells us that anything raised to the 0 power is 1. But actually, I guess it would be better just to, well, we could use exponent rule number 7, but we know that the logarithm is just going to be 0 because these bases are the same. So I guess you don't really have to use exponent rule number 7. So 10 times 0 is 0. So we have 0 decibels. So what does 0 decibels mean? It means that you can't hear the sound. It's right at that point where humans are able to hear but not hear. So if you got that right, excellent. Try number 17. When you come back, we'll do it together. Okay, we're back. So L of 10 to the negative 9th is equal to 10 times log base 10 of 10 to the 12th times 10 to the negative 9th. And we're going to use exponent rule number 1 to multiply those powers, and we get 10 to the 3rd power. And this entire logarithm becomes 3. So we have 10 times 3, which is 30 decibels. So we can hear 30 decimals. Any positive number, if you have good hearing, then any positive decibel is going to be a measurement of a sound that we can hear. If it's 0 or negative, then we're not gonna hear it. So if you got that right, excellent. Go ahead and try number 18. When you come back, we'll do it together. Alright, we're back. So L of 10 to the negative 11th is equal to 10 times log base 10 of 10 to the 12th times 10 to the negative 11th. And we need to use exponent rule number 1 because we're given our intensity in it's in the form of a base 10 power. So we have 10 to the 1 power, and this entire logarithm just becomes 1 because remember logarithm property 2, we talked about that. Again, if you want a picture of that, go ahead and get that picture there. So we have 10 times 1, which is equal to 10 decibels. So if you got that right, excellent. So we can barely hear that, but we can hear, if you have good hearing, we're going to barely hear that. So if you got those right, excellent. So now we're going to go in the opposite direction. Now we're given the loudness, and we're asked to find the intensity of the sound. So we're going backwards here. So let's write our equation for the loudness. Physicists define the loudness to be 10 times log base 10 of 10 to the 12th times the intensity of the sound. So now all we have to do is plug in the numbers that we know and solve for the numbers that we don't know. So we know the loudness is 24 decibels. So L of x is just 24. So now we're going to solve this equation, but we have to isolate the logarithm first. It's not isolated because we have a purple 10 there. So let's divide both sides by 10. Now students tend to get a little confused by this, so I'm going to show this division. You don't have to show it, but I'm going to show it anyway. So dividing both sides by 10, and we get 2.4 is equal to log of 10 to the 12th x. Log base 10 of 10 to the 12x. So we can't really solve this unless we know what the base is of the logarithm. but there is no base, right? So what is it? Well, again, that's a special base, so we have special notation. Log of this expression means log base 10. That's very important. Okay, so now you might think, well, these bases are the same, so we can just make this entire logarithm equal to 12. But the problem is we have an x next to this exponential expression here, so we can't do that. We have a property that tells us log base b of b to the x is equal to x, but the property does not tell us that log base b of b to the x times some number, which we'll call y, it doesn't say that that's equal to x. So we can't do that. So what do we do? Well, there's nothing we can do except translate this to an exponential equation. So what is the base? The base is that little subscript there. What is the exponent? The exponent is what the logarithm is equal to. And whatever's in the log function goes on the other side of the equation. So it is 10 to the 12th times x. So that's just basic stuff when it comes to converting from logarithmic form to exponential form. That's the most important thing when dealing with logarithms or exponential expressions. You have to be able to translate back and forth. If you can't do that, then there's no way they're going to have a chance to work with these types of problems. Okay, so now what do we do? Well, we could use a calculator, but let's simplify this first because we have a lot of skills that we learned in my intermediate algebra course to deal with exponential expressions. So let's divide both sides by 10 to the 12th. You don't have to solve it this way, but this is a good way to solve it. And then we have x is equal to, and remember when you're dividing powers, you just subtract the exponents. So what is 2.4 minus 12? 2.4 minus 12. Well, that's negative 9.6. So 10 to the negative 9.6. So this is going to be a very small number, and because it's going to be such a small number, we want to just leave it like that. Leave it in that form, and we can write watts per square meter. So that is the answer. That's the intensity of the sound that would create 24 decibels. Okay, so let's try some more of these problems. Now we have 51 decibels. The loudness of sound is equal to this expression. L of x is 51. And remember, what you're going to see as the initial equation doesn't have a base on the logarithm. So I just want you to be completely aware of that. So you have to create your own base there so we know what's happening here. So now we're going to divide both sides by 10, and we get 5.1 is equal to log base 10 of 10 to the 12th times x. Well, now we can't do anything. We're stuck unless we translate to an exponential equation. So remember, this number is always the base, and this number is the exponent. Whatever the logarithm is equal to, that's the exponent. And whatever's in the log function, that goes on the other side of the equation. So now we're going to divide both sides of the equation by 10 to the 12th power, and you don't have to show the work with this, but I'm going to show it because it may be a little intimidating to do this So now we get 10 to the negative 6.9, it looks like. And we can just say watts per square meters, and we're done. So we found the intensity of the sound that would create 51 decibels of loudness. All right. So let's do one more of these before you try one on your own. So again, our formula that we're given is the following. We don't have a base, but remember, if there's no base written in the logarithm, that means you have to write base 10. And they tell us that we have 130 decibels of sound. And so what do? We just divide both sides by 10. And we get 13 is equal to log base 10 of 10 to the 12th x. And now we can't really do anything unless we know how to translate to an exponential expression. The base is always that number here. The exponent is what the logarithm is equal to, and whatever is in the log function, that goes on the other side. All right. So now let's divide both sides by 10 to the 12th. And we're going to use exponent rule number 2. And by the way, you can write exponent rule number 2 if you want. Just as I didn't ask you to do that in these problems, but it's probably good to note that we're using exponent rule number 2. Subtract the exponents and we get 10 to the first power, and now we're going to use exponent rule number 6, which tells us that anything raised to the first power is just whatever the number is, and that's in watts per square meter. So if you got that right, excellent. So I want you to take a picture of all this information here, and then I want you to try number 22. When you come back, we'll do it together. Okay, we're back. So we have the loudness of sound defined for us. It's equal to this expression. And we know that the loudness of the sound that we're interested in is 111 decibels. But before we do that, just be aware that when you see a logarithm without a base, it's base 10. So the decibel level is 111. We're going to divide both sides by 10, and we get 11.1 is equal to log base 10 of 10 to the 12x. Now we're going to translate to an exponential expression. This number is always the base. Whatever the logarithm is equal to is always the exponent. And whatever's in the log function goes on the other side. So now, just to make things clear, I'm going to show the division. We're dividing both sides by 10 to the 12th. And we're going to use exponent rule number 2, which tells us that when we divide powers, we subtract the exponent. So we're going to have 10 to the negative 0.9, because 11.1 minus 12 is negative 0.9, and this number is manageable if we use our calculators. Some of these numbers are really, really small or really, really big. But let's see what happens when we put this into our calculator. So enter 10, and then the upside down V button is your exponent button. That's at the middle right of your TI-84 plus. And then enter negative 0.9. And we get approximately 0.12589 watts per square meter. And I don't think these problems tell us that we need to round to a certain number. No, they don't. So we can use our own discretion when rounding. Okay, so if you got that right, excellent. So I want you to try number 23. Write the Roman numeral of the exponent rule that you use in the margin. I don't know if I specified. Yeah, I didn't say to do that, but it's probably best to write the Roman numeral of the exponent rule that you're using. Try number 23. When you come back, we'll do it together. Okay, we're back, so let's write our equation. I know that we have the equation at the left, but I'm just being thorough here so we know exactly what is happening. And again, one of the most important things that we need to remember is that when there's no base written in the logarithm, it's assumed to be 10. So now the loudness is 90 decibels. So we're plugging in 90 for L of x. Then we're going to divide both sides by 10. And we get 9 is equal to log base 10 of 10 to the 12th times x. And at this point we're stuck. There's nothing we can really do unless we translate from a logarithmic equation to an exponential equation. So the base is always that little number there, and the exponent is whatever the logarithm is equal to, because remember that's what a logarithm is. It's an exponent, and whatever's in the log function, that goes on the other side of the equation. Again, translating back and forth from logarithmic form to exponential form is crucial for you to be able to perform when it comes to these problems. So we're dealing with some very big numbers here. Now we're going to divide both sides of the equation by 10 to the 12th as we did in the previous problems. And so x is equal to 10 to the negative third, and we used exponent rule number 2. When we divide powers, we subtract the exponents. Now we could just enter this into our calculator as we did with this problem, but let's just demonstrate exponent rule number 8. What this means is 1 over 10 to the positive third, and that would be equal to 1 over 1,000, and that's equal to 0.001. To be honest with you, I don't really care how you write it. You could really write it in any of these forms, but this form is probably the best. This form is okay, but it's not as good as this form here. Now you'll notice that a lot of these numbers are very, very small or very, very large. Here's a number that's really, really small. Another number here that's pretty small. These numbers are manageable, but this number is also manageable, so we don't have to write it with a base 10, so we can just write it in this form. Now again, if you wrote it in a different form, that's okay. but I just want you to see the possible options for how to write the answer. So if you got that right, excellent. So I want you to try number 24. And I'm going to write the equation for you. So the loudness is equal to 10 times log 10 to the 12 times x. So go and attempt number 24. When you come back, we'll do it together. Alright, we're back. So when you don't see a base in a logarithm, it's assumed to be base 10. The only exception to that is when you see ln x. You don't see a base there either, but that's assumed to be log base e of x. So I'm just talking about the log notation. So we're told that the loudness is 12 decibels. And we're going to divide both sides by 10, and we get 1.2 is equal to log base 10 of 10 to the 12 times x. And at this point, we're stuck. There's nothing we can do unless we know how to translate a logarithmic equation to an exponential. So we're going to write the base. That number is the base. That little number is always the base. The exponent is whatever the logarithm is equal to, because that's what a logarithm is, and whatever's in the log function is on the other side. Okay, so now we're going to divide both sides. You don't have to show the division if you don't want to, but I'm going to show it because this tends to sometimes confuse students when you have weird expressions that you're dividing. So we're now going to use exponent rule number 2, which means we're going to subtract the exponent. So we get 10 to the negative 10.8. So that's a very, very small number. And it's so small that we're going to just want to keep it in this form. We could use something called scientific notation to write that, but we don't want to get mixed up with that right now. This is not a science course. So there you go. If you got that right, excellent. So now we're going to move on to an application that uses base E. Loudness of sound is measured with a base 10 logarithm. The magnitude of earthquakes that we did in the my intermediate algebra course, they're base 10 logarithms. And the pH of water, the acidity of water, is a base 10 logarithm. But we also have base E logarithms in nature, and we're going to study those quite a bit in the next class. But we're also going to study the financial application in this class. But before we do that, we need to review the concept of interest. This is defined to be simple interest, and we don't really use that much in the math curriculum, but we do see compound interest, and it is somewhat important in the study of finance. So we're not going to go over simple interest much, but we are going to do some problems reviewing compound interest. So if you've ever heard somebody say that something is compounded by something, that means that it's getting better or worse based on the change that has occurred. So in finance, let's say that you're putting your money in the bank and you're making a certain amount of interest in, let's say, a year. So let's say you have $1,000 and you made $20 interest. Well, for the next year, you're now going to make interest on that $1,020. So you're adding the $20 and then making interest on not just the $1,000 but also the $20 that you added. And so then you make more interest in the next year, and then you create interest based on the money that you made in the first 2 years from interest, along with the original 1,000. So that's compounding interest. So compound interest is much more involved. It's a much more complicated topic than simple interest. Compound interest is this red formula here. So we learned this in my intermediate algebra course, and we're not going to go through it as thoroughly as we did in my intermediate algebra course, but we do have to review this a little bit. So let's do a practice problem. It's easier to do a problem than to explain the formula. So if $7,592 is deposited in a bank account paying a 3% annual interest rate compounded monthly, how much money will be in the account in 2 years? Assume that there are no withdrawals or additional deposits. So A is the number we're looking for. That's the amount of money in the account. If you deposit a certain amount of money, P, and the interest rate is some R value that's written in decimal form, and you're compounding n times per year for a certain amount of time, in years. So it's very important to understand that n is defined to be the number of times that you compound per year. Is that understood? N is always the number of compounding events per year. It's always per year. That's very important to understand. N is per year. It doesn't matter what type of problem you're doing. If you're using this formula, then n is the number of times you compound per year. So, what is the principal, the amount that you deposited? Well, that's $7,592. What is the interest rate? Well, it says 3% annual interest rate, so we're going to write that in decimal form. And how many times are we compounding? Well, it says compounded monthly. So how many times per year would monthly be? Well, that'd be 12 months in a year. And then how long are we doing this? 2 years. So that's it. That's all we have to do is calculate that expression there. So let's do 0.03 divided by 12 first. And we get 0.0025. And 12 times 2 is 24, so I'm going to go ahead and calculate that. This is all review stuff, by the way, so you've seen this before. And then I'm going to add these numbers here. I'm going to go here, so that's 1.0025 to the 24th. And let's see if I have enough room here. So then we're going to calculate this expression here. So 1.0025 to the 24th power, and then enter. So you want to use the upside down V button in your calculator, your TI-84 plus. It's at the middle right. So we have 7,592 times roughly 1.06175, and I'm going to put a ... meaning you want to keep that number in your calculator. So let's find some more room. So the final answer is going to be that number times 7,592. And so how much money do we have in the account? We have roughly $8,060.86. And we need to write a dollar symbol, obviously. So there you go. That's how we use that formula. So I want you to try number 26 and be aware that compounding quarterly means compounding 4 times per year, just to clarify that. So go ahead and try number 26. When you come back, we'll do it together. Okay, we're back. If you got that right, excellent. Okay, so that was compound interest. We're not going to go over that in a lot of detail because you can go back to my intermediate algebra course and review that if you'd like to. But we're going to move on to continuous compounding because it's an application of base E exponential expressions. So we have our compound interest formula here, and if we do a lot of algebra, we can change the form of that expression, and you're perfectly capable of understanding this algebra, but you don't really need to. I don't want to intimidate you with all this stuff here, but all we're doing is using exponent rule number 5 in reverse, and then we're making a fraction complex. So we start with this fraction, and if we want to make it complex, we can actually turn it into that expression there, because 1 over n over r is the same thing as 1 divided by n over r, which is the same thing as 1 times r over n, which is the same thing as r over n. Alright, so I know that's really tricky, but this is advanced mathematics here, so 1 over r, n over r is the same thing as r over n. I know that's very, very tricky, but sometimes mathematicians do that. And so then we do something even more tricky. We change n to n over r times r, because if you multiply these, the r's cancel out. And again, I know that's a lot of tricky stuff there. You don't have to really know that stuff right now, or really ever. But that's the algebra. So we change the form of this expression to this expression over here. Why do we do that? Well, mathematicians have they've noticed that as you make n bigger and bigger, remember, n is the number of times you're compounding per year. If you make it 1,000, then a billion, then a trillion, then a quadrillion. If you keep making it bigger and bigger, then this expression inside here, and I'm going to highlight that expression, this expression here approaches some special number. And you would think that as n gets bigger, that yellow expression would just would get bigger itself. It would never stop increasing. It would just go on and approach infinity, but it actually doesn't. Technically, it keeps increasing, but it approaches a number. It doesn't go off into infinity. It approaches a number. And that number is 2.71828. And what do we call that number? We call that number E. So that's that special number. So if you compound 1,000,000 times, or 1,000,000,000 times, or a quadrillion times, then for all intents and purposes, we can just say that this yellow expression here just equals whatever this special number is. So we just take this yellow expression up here and we just turn it into that number. And we call this continuous compounding because n is so large that we might as well just consider it to be approaching infinity. and then we turn this yellow expression into this number, and that number is just e again. So and then the t and the r, they multiply because we factored out that t, and so we're left with this expression down here. So this is the formula that we use when we compound interest continuously. So it means that we're compounding an infinite number of times per year. Now I said an infinite number. Infinity is not really a number, but you know what I mean. We compound it continuously every millisecond, a bazillion times every millisecond, quadrillion times every millisecond, and more. That's what continuous compounding means. It's literally infinity. We don't even know the number of times we're compounding. So there's our formula, and so this is an application of base E exponential expressions. So we studied the loudness of sound. That was an application of base 10, and now we're going to use an application for base E expressions. So it says here, if interest is compounded continuously for 2 years at 3%, at a 3% rate, how much would a $4,000 investment grow to? So let's write our formula. And remember, P represents the amount of money that we're depositing in the bank. And so we put $4,000 in there, that's P. And E is just a constant, and we always write the interest rate as a decimal, and this occurred for 2 years. So we have 4,000 times E to the 0.06, and now we go to the calculator. So if you're using a TI-84 Plus, you're going to press the blue second button and then the LN button at the middle left. So you should have an E with a box there. And then you're going to enter 0.06 and press enter. So we have 4,000 times 1.0618, and you can keep that in your calculator and then multiply that by 4,000, and we get $4,247.35. We're always going to round off to the nearest cent because we can't have a fraction of a cent. Okay, so there you go. There's an application of base E exponential expressions. Let's do one more of these before you try one on your own. So how much are we depositing? $541. What is the interest rate? In decimal form, it's 0.0007, and we're doing this for 10 years. Whoops, sorry. Okay, so now we have 541 e to the 0.07. We multiply by, actually that would be 0.007. When you multiply by 10, you just move the decimal one place to the left. And again, we're going to push the blue second button and then the LN button, and then 0.007, enter, and we get 541 times 1.007 and dot dot dot. So keep that number in your calculator, multiply by 541, and we get $544.80. So again, that's an application of base E exponential expressions. So I want you to try number 29. When you come back, we'll do it together. Okay, we're back, and 87 cents. So if you got that right, excellent. Go ahead and try number 30. When you come back, we'll do it together. Okay, we're back. All right. So if you got that right, good job. So again, loudness was an application of base 10 logarithms, and interest compounded continuously was an application of base E exponential expressions. Okay, so let's do some problems where we are going to need the natural logarithm. So it says here, if an $18,293 investment grows to $40,368 in 9 years, what interest rate was applied if it was compounded continuously? So interest compounded continuously is not going to be this formula. This is when you have a finite number of compounding events. We're not going to use that. We're going to use this formula because there's an infinite compounding events. So what we're going to do is plug in the numbers that we know and solve for the number that we don't know. So we know that the investment grows to $40,368, and it started at $18,293. And we know that the investment grew to that number in 9 years. So what we're looking for is the interest rate. It says what interest rate was applied. So what we're going to do is solve for the exponential expression, and this is kind of a lot to have to write just to modify one thing, but just so you can be more familiar with this expression, I'm going to change these around. So we're solving an exponential equation, and this equation is a lot easier than the equations that we did at the beginning of the class, because most of the equation is already solved for us. So what I'm going to do is solve for this exponential expression, and I'm going to divide both sides by 18,293 in order to isolate the exponential expression. So I'm going to move this over here. And so let's use our calculators. 40,368 divided by 18,293 is approximately 2.2067, and we can write dot dot dot. That means keep that in your calculator. And I'm going to write this up here so it's easier to see. And now we're stuck. There's nothing we can do, right? Unless we know how to translate to an exponential, or excuse me, unless we know how to translate to a logarithmic expression. We need our calculator to solve this. So we need to ask the calculator what that exponent would be. And what we do is we enter log base E of that number that we still have in our calculators. But remember, when we tell our calculator to do that, we don't use log base E, we use ln. When we have that special base, that base E, we use ln. So in your TI-84 Plus, or whatever graphing calculator you're using, you want to press the ln button. It's at the middle left for those using a TI-84 Plus. And then I want you to push the blue second button at the upper left, and then at the very bottom it says a negative symbol sign with parentheses around it that says ANS in blue writing. Press that button at the bottom right. It's a negative symbol at the bottom right with parentheses around it, and when you press that it should say ANS, answer. Then press enter. And so now we know that the exponent in that equation has to be equal to 0.79 0.15 and dot dot dot. So you want to keep that number in your calculator, and then you're going to divide that by 9, and we have our interest rate. But interest is always written, at least in finance, interest is always written as a percent. And I'm going to carry out a few more decimals here. So let's move up a little bit. So all we have to do now is write our number as a percent, and that'll be the interest rate. So 8.79%, we can just round it to the nearest hundredth of a percent. It doesn't tell us what to round to, so you can use your own discretion with that. So there you go. Okay. So let's try another one of these before you try one on your own. So it says here, an investment grows from $5,023.14 to $6,112.14 at 3.7% annual interest, compounded continuously. How much time passed during this growth? So again, we're going to use our continuous compounding formula. And it says that our investment grew to $6,112.14, and it started at $5,023.14. The interest rate was 3.7%, but we have to write it as a decimal. Very important that you remember that. You have to write the interest as a decimal. So we're looking for the amount of time that passed. So this is an exponential equation, and we need to isolate the exponential expression. So we're going to divide both sides by 5023.14. Let me copy all this. So I'm going to divide both sides by 5023.14. And so let's do that in the calculator. So we get 1.21679 dot dot dot. So keep that number in your calculator. And so at this point we're stuck. There's nothing that we can do unless we know what to tell the calculator, because we need to find this number, and the calculator is going to tell us. So what is that number? Well, we enter log base e of whatever's on the other side of the equation, and that number should still be in your calculator. Okay, so we're out of room, but don't panic. Whenever you run out of room, don't panic. So we're going to go up here, and remember, when we have log base e, we don't write log base e, we write ln. And this number should still be in your calculator. So now press ln at the bottom left, and then the blue second button, and then the button at the bottom right with the negative symbol with parentheses around it, and then it should say ANS, and press enter. So natural log of that number is approximately equal to 0.19622 dot dot dot. So keep that in your calculator, then divide that by 0.037. So divided by 0.037, enter. And the time that passed is 5.3, And what are the units? Well, it says that the interest rate is annual. So this is going to be 5.3 years approximately. And we can say approximately equal to, because that's a rounded off number. Okay, so we had to use the natural logarithm. That is an application of natural logarithm. So I want you to try number 33. And when you come back, we'll do it together. You can take a picture of all this information if you'd like. So try 33. When you come back, we'll do it together. Okay, we're back. So if you got that right, awesome. So again, these are applications of natural logarithms. So try number 34. When you come back, we'll do it together. All right, we're back. All right. And why is it years? Well, because it says annual interest rate. Okay, so if you got that right, perfect. Good job. So now we're going to go to something called change of base. This is the last logarithm property we're going to learn in my curriculum. So this is logarithm property 9. So here's a list of all the logarithm properties that we learned. Some of these are more important than others, but you can reference that if you want. Change of base is not really as important as it used to be, because it used to be that calculators were not able to find the values of any kind of logarithm with any base. It used to be that calculators would only be programmed with base 10 capability or base E capability, and so this formula was used very, very frequently because it's used to change the base of the logarithm. Notice here we have a base A logarithm, right? That's a base A logarithm. But on the other side of the equation, we have a base K logarithm. Where did K come from? There's no K on this side, so what is K? Well, K is actually any base we want it to be. I know that sounds strange, but yes, K can be any number you want it to be. So you can change a logarithmic expression into an expression with any base for the logarithm, and that's beneficial if our calculators only use base 10 or base E. And now if you have a graphing calculator that was made in the last 10 years, probably even the last 15 years, or maybe in the last 20 years, then your calculator should be able to calculate any logarithm. So to show you this in the TI-84 Plus, I want you to push the green alpha button, and then the window button at the upper left. It's the table set F2 button, the window button. And then I want you to go down to number 5 and then press enter on number 5, and you should see this. You should see log with a base. So this allows you to calculate any logarithm. It doesn't have to be a particular base, doesn't have to be base 10 or base E. So again, we don't really need this, and that's why I didn't really focus on it much. But why are we learning this now? Well, because it's very possible that you may see a problem in the curriculum in the college that you attend, or wherever you attend, if you're going to a high school or something. It's very probable that you may see this, so I want you to be familiar with it. And again, if you have a calculator that only uses base E or base 10, then you can't find the value of any logarithm unless you change the base. Now we can prove this property very easily using the other logarithm properties that we used, or that we learned, but you don't really have to prove it, and we don't really have time to do that right now. So it says here, use logarithm property 9 to change each logarithm to a quotient of logarithms with the indicated base. So it wants us to use base 5, and by the way, you can get a picture of this if you'd like. So we want to write this with the base 5, so it's going to be log base 5 of the number here divided by log of the same base, except that number, the base of the logarithm, and that's it, we're done. So pretty easy, right? So if our calculators could not compute base 6 logarithms, then we could change it to a base 5 logarithm. That's just a hypothetical situation. So now we have, we want base 3. The problem tells us to change it to a base 3 logarithm, so it's going to be log base 3 of 7 over log base 3 of 8. That easy. So this is not something that's really that difficult. So it wants us to change this logarithm to a base 9 logarithm. We have a base 4 logarithm right now. So it's going to be log base 9 of 5 over log base 9 of 4. That's it. So again, you might want to get a picture of that logarithm property up there. So we have a base 98 logarithm. We're going to change it to a base 49 logarithm. And there you go. Okay, so I want you to try number 39. When you come back, we'll do it together. We're just getting used to this logarithm formula. Okay, we're back. We have a base 7 logarithm. We want to change it to a base 2 logarithm. And so we're left with the following expression. If you got that right, excellent. Go ahead and try number 40. When you come back, we'll do it together. Alright, we're back. We have a base 5 logarithm. We want to change to a base 4 logarithm. It'd be nice if we didn't have a fraction, but we can't really avoid that. That's just how the formula works. Okay, so go ahead and try number 42. When you come back, we'll do it together. Alright, we're back. We have a base 3 logarithm. We're going to change to base 8. Or at least an expression with base 8 logarithms. Okay, if you got that right, good job. So now we're going to assume that we're using calculators that only have base E and base 10 capability. So it says use your calculator's base 10 logarithm button and the change of base formula to find the value of each logarithm below. So if we're going to use the log base 10 button, then we have to use base 10 logarithms, obviously. But remember, when we write a base 10 logarithm, we don't have to write the base. We can just write log 7 over log 3. So press the green alpha button, the y equals button, and the enter button, and your TI-84 plus, and then the LOG button, and then 7, right parenthesis, and then down arrow key, LOG 3, and then the right parenthesis button, and then the right arrow key. We should have log 7 over log 3. Press enter, and we get 1.47, actually 1.77. Says round to the nearest 10,000th. So 1.7712. And we should say approximately equal to. So again, if we assume that we only have base 10 capability, then we're going to use the change of base formula to calculate the value of the logarithm. So let's try it again. We don't have to do this intermediate step as long as we know we're using base 10 logarithms. So the green alpha button, the y equals button, enter. And then log 2, right parenthesis, down arrow key, log 5, right parenthesis, right arrow key. So you should have log 2 over log 5. Press enter. And we get approximately 0.4307. So again, you may come across this in the math curriculum. In fact, it's almost a guarantee you're going to see change of base problems like this, even though your calculator doesn't really, it doesn't have that deficiency. You're going to see this in the curriculum. So try number 45. Again, you want to use the base 10 logarithm button in your calculator that says log. And the change of base formula. We're assuming that our calculators can't perform with log base 9 logarithms. So try 45. When you come back, we'll do it together. Alright, we're back, so we're going to change to log 32 over log 9. Again, press the green alpha button, the y equals button, and the enter button, and then log 32, right parenthesis, down arrow key, log 9, right parenthesis, right arrow key. So log 32 over log 9. We can approximate that as 1.5773. If you got that right, excellent. Try number 46. When you come back, we'll do it together. Okay, we're back. So this is going to be log 6 over log 8. Again, these are base 10 logarithms, but you don't have to write 10. So the green alpha button, the y equals button, enter. Then the log button and 6, right parenthesis button, down arrow key, log 8, right parenthesis, right arrow key. So log 6 over log 8 is approximately 0.8617. So if you got that right, excellent. Okay, so now we're going to assume that again, our calculators only have base 10 or base E capability. So this time we're going to use base E for our logarithms. So again, pretending that our calculator can't do base 4, we're going to change to log base E using the change of base formula. But remember, you don't have to write log base E, you can just write ln, because it's kind of tedious to have to write log base E. So the green alpha button, y equals button, enter, and then you're going to push the ln button right below the log button. And we get approximately 1.403, and it says round to the nearest hundredth. So I can just round to 1.4. Okay, so let's try it again. But this time we don't have to write this step. We can just go straight to ln2 over ln6. The green alpha button, y equals button, enter. And ln2, right parenthesis button, down arrow key, ln6, right parenthesis, right arrow key, enter. And we get approximately 0.39 if we're rounding to the nearest hundredth. So I want you to try number 49. When you come back, we'll do it together. Alright, we're back. So this is going to be ln 11 over ln 8, which is going to be approximately equal to green alpha button, y equals button, enter. ln 11 over ln 8. Press enter, and we get approximately 1.15. So if you got that right, excellent. Go ahead and try number 50. When you come back, we'll do it together. Alright, we're back. So this is going to be ln 17 over ln 15, which is approximately equal to, let's enter it into the calculator. And we're going to get approximately 1.05 if we round to the nearest hundredth. So if you got that right, good. So that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and number 4 and number 5 and number 6 and number 7 and number 8 and number 9, number 10 and number 11. But don't go before you get your homework. Remember, the homework is not optional. Here's the first screenshot of the homework, and screenshot number 2 and number 3 and number 4 and number 5, and here's the answers to the homework. Remember, it's not enough to attempt the homework. It must be done correctly and completely and neatly and kept in order in your binder. So get that homework done, and I'll look forward to seeing you in the next class.